Yes, it is. Great. So now we'll discuss continuity. Oh no, I have one more thing. Squeeze theorem. Okay, so far we have bounded, like we have tried to find limits by immediately evaluating them, right? We have tried finding limits of function by evaluating the limits. Of course, it does not cover all the cases, but sometimes I do not have too much information to determine the limit of a function. So the squeeze theorem comes in handy. So what is the squeeze theorem? Okay, now I will not give you an introductory statement that f and g are defined around in an open interval containing a number a except at possibly a, but I will just say if f of x g of x for all x different than a, and the limits of the function that are bounding g both exist and are equal, to a number L. What can you say about the limit of g? So basically h goes to L and f goes to L. If g is squeezed in between, where must g go to? L. That's it. Okay? That's the squeeze theorem. Let's give an application. Oops, that's happening today. Where's the let me write here, actually. Example. Suppose that f of x is between x squared and minus x squared. Okay? F is a function such that f of x is between x squared and minus x squared. X squared above, minus x squared on the bottom, below. What can you say about the limit as x approaches 0 of f of x? X squared, when x approaches 0, where does it go to? 0. Minus x squared, when x approaches 0, where does it go to? 0. By the squeeze theorem, f of x, the limit as x approaches 0 of f of x is equal to 0. Okay? You double check that. Yes? Yeah. Yeah, thank you for the question. So there are two things. When I'm evaluating for example, limits, right? I write limit as x goes to something, blah, blah, blah. You still have to write down limit, okay? You cannot just not, omit the limit, okay? When I'm writing limits, okay? Each time you miss that, you lose a mark. Okay, so say the question is on 5 marks and you miss it 3 times, you lose like 3 marks. Okay? So it's very important. Well, I mean, I don't want to say how much you lose, but you will lose marks. Okay, maybe 3 is a bit much, but yeah. Okay, and if you're using a theorem, guys, you have to state what the theorem is. Okay, you have to clearly state it. Great. Let's give another example. Okay, great. Awesome. Fine. Of course, here, let me just add this for all x equals. Okay. For all real number x. Okay, great. Find the limit as x approaches 0 of x squared sine squared 1 over x. What's the first thing you try to do when you have an expression? You try to plug in, right? I mean, in general, that's what you try to do. Now, can you plug in 0 in this expression? No. Okay, so this function is not defined as 0, is it? F of x is x squared sine squared 1 over x. Is it defined as 0? No, right? Sine 1 over x. So sine 1 over 0. Can I write 1 over 0? Does that mean anything? No. Great. Now, how do I find this limit? Technically, x squared will go to 0, right? Limit of x goes to 0 of x squared is 0. And the limit of x approaches 0 of sine squared 1 over x. What is that? Can you determine this? Not really. It's a bit difficult to determine because it doesn't exist, in fact. Because sine 1 over x, or let's it doesn't matter. But let's keep it here. Sine 1 over x keeps oscillating between -1 and 1. And when x is near 0, it oscillates fast. Did you ever see that? So it oscillates very fast. Okay? Does that exist? Try to plot on a calculator. Try to see how to plot on a calculator. Try to plot on a calculator to see what the graph looks like. And you will see that the limit at x equals 0 doesn't exist. But what do we know about sine 1 over x? Sine of something is between what and what? Between 1 and -1. So we know that for all x different than 0, sine 1 over x is between 1 and -1. Is that clear or not? Yes or no? Now, x squared is a positive quantity, isn't it? It's a non-negative quantity. You agree or not? So I can multiply by x squared here and here without changing the sign of my inequalities. You agree or not? Now, can I conclude or not? Can I use the Squeeze theorem here? Where does the right one go as x approaches 0? Where does the left one go as x approaches 0? So the middle, where does it go? 0. So, by Squeeze, okay. Rich knows that the limit as x approaches 0, sine 1 over x not okay, great. Awesome. Now, we're done with the Squeeze theorem. We'll start a new chapter, or a new section, which is called continuity. Okay? Everything clear? Any questions? Yes, sir.
Sorry, I just how you went from -1 to -x squared.
Multiply. So what do you want to get? You want to get the limit of x squared sine 1 over x, right?
Yeah.
Multiply both sides by, multiply the two inequalities by x squared. X squared is a positive number, so it doesn't change the sign of the inequality. Yes? A question? Yeah? No? Yeah. Would you please? Yeah.
Do you say the same thing here with the domain that you have given, or?
Pardon me? Guys. Yeah.
When you said for all XCR up above, do you say the same thing here with the domain?
No, it's for all x different than 0.
Okay.
Okay? X and R, have you seen the word R? R is the real number, right? This symbol, like the euro, belongs to, right? Have you seen this before? Yeah, okay, great. Awesome. Yeah, what was your question? Did I answer it?
So do you have to give a domain and say X is all reals except for when?
Yeah, I mean, this is the most important thing. Just X, when X is near 0, I mean, this holds true for all X different than 0, right? You don't need it for all X, you just need it near 0, okay? Near 0 but not equal to 0. And in that case, that's fine. Yeah. Okay, now let's start to talk about continuity. Great. Great. Seems the cold season has started. Anyway. Great. Okay, we're still. Wait, what happened? Oh, okay. Okay, great. Continuity. Okay. Now a definition. Out of a class of 400, how likely is it that many have a cold? Anyway. Yeah, it's starting now. September, October, usually it's the worst. I don't know about November, but September, October is. I mean, I think I caught COVID in August. Yeah, I think it's wasn't very pleasant, but anyway. Okay, let's start by definition. Great. Okay, so before we move on, I think we're going at a very good pace, more or less fast, which is fine. It's not a big deal. That's going to save us some time at the end to spend more time on the material, on the harder materials. But is there any questions on the things we have covered before? Yes?
Is there any way you can do one more example of the squeeze theorem?
Yeah, sure. Let's do one more example. So what's your favorite number? Yeah? Yeah, your favorite number?
Let's say 31.
31, okay. Okay, let's try something. Great. X going to 0. Okay? First of all, can I apply the product rule here? Cos 31 over x, it will just oscillate very quickly. Okay, between -1 and 1, and very quickly. So it won't converge. Right? Do you know that cos x, does it have a value when x goes to infinity? Or it could really take any value between -1 and 1. Cos is periodic, right? So cos x can technically does not have a limit, when x is very large. Now, if x is very large, or if x is very small, then 1 over x is very large, right? Plus infinity or negative infinity. You should see it this way. I mean, we'll see this more in details in the coming weeks. But the idea is that if this x is very small, somewhere near 0, then this 31 over x is a very big number, positive or negative, right? So cos 1 over x will not have a limit. Okay? Is that clear? Sketch it on the calculator, or in a graph, or on whatever program you're using, and you will see that it does not have a limit. So really, I cannot apply the product rule. But what do I know about cos 31 over x? It's bounded between two values. What are these two values? -1 and 1. Okay, now, what can I do? I need to let this x to the 4 cos 31 over x appear. What do you suggest? Yeah? By x to the 4. And why can I do that? Sure, but why can I do that? Like, why I multiply by 2? Yeah, sure. Yeah, okay. But do you need to reverse the inequalities, or not really? No. Why? Because x to the 4 is positive, right? For x is greater than 0. And then the limit is equal to 0. So by squeeze theorem, let me write this here. Okay? X to the, what about what I said? Cos 31 over x is equal to 0. Is that good? Is that fine? Sorry, yeah, go ahead. Where the limit? Sure. Sure. Let's see. Suppose that, let's say, f of x okay? What is the limit as x approaches 1 of f of x? I'll let you do that as an exercise, but try that. What is that? As x approaches 1, x squared, where does it go to? 1. When x approaches 1, 2x minus 1, where does it go to? 1. So the f of x, where will it go to? 1. Okay, is that clear? Yeah? Yes, sir.
Would there be any situation where we have to get an inequality?
That's a good question. I mean, this could happen technically, but maybe not in this course. I mean, it could be done, right? I mean, we'll see things like that happen. Okay? But yeah, very good question. Yes. So you mean by bounding tan? In general, tan, when you want to bound it, you cannot bound tan, right? And the limit, yeah, you cannot bound tan in general. Okay? It just usually when you have cosine of something you cannot evaluate, only then would you use, well, not only then, but it's a good sign that you need to use the squeeze theorem. Okay? When you cannot use the limit law and you have a cosine, it's just trial and error. Trial and error means, and how do you get used to this idea when to use squeeze theorem and when not? By constant practice. Practice and then you'll, okay? Yeah? But I think there is squeeze theorem, right? I think I posted questions on that. Yeah? I posted questions on squeeze. Did I? In the suggested problems, yeah. Okay. So it must be in one of the sections. Okay, great. Awesome. Yes? Would you please raise your voice? Guys, yes. Yes, both limits on the right and on the top and on the bottom, yes, they have to be equal. Pardon me? What's the reason for that? That's a good question. So, I mean, the way they explained it to me, when I was in high school, they explained it in French. In French, it's called Theorem des gendarmes. So the policeman theorem. Okay? Usually, so I'm a thief, for example, and there's a policeman who's taking me to jail. Okay? So if he's taking me from, if he's pulling me here, I can still escape, right? If the one here is going to jail, then I may just escape. Now, if there is a policeman pushing me to jail here, right? He's below, like he's behind me, and he's pushing me to jail. I can still escape. Now, if I have a policeman here and a policeman here, and they're both going to the same place to jail, then I'm going to jail. Okay? That's how they explain it to me. It's a weird explanation, but yeah, it's called Theorem des gendarmes in French. Yes. I don't know, anyone has seen this explanation before? Theorem des gendarmes. Anybody has heard this? No? Okay. Or Theorem du sandwich. Sandwich theorem. Yeah. Okay, yeah.
For your first one, you put for all real numbers. Should we be writing that for the last question that we did as well?
Where? This one?
Yeah.
Is this one defined as 0?
Wait, no, sorry. The first one is the top board. You put for all real numbers.
Yeah, here, yeah.
Should we be writing that in our answer for the last one as well?
Here?
No, for the one that you wrote proposed.
Oh, yeah, yes, thanks.
We
Yeah.
should be writing
Yeah,
that?
I'll give it to you.
Okay, we're to make sure that
I'll give it to you. Okay. In R. Yes, sir. Oh, it's glitching. No. Yes. Sorry? Where? Here? So what did I have? This is G, right? This is F, and this is H. Your G should always be in the middle. Okay? Okay, is F less or equal than G? Is G less or equal than H? G is less or equal than H, right? G is bigger or equal to F. Right? And then let's say, the squeeze theorem. F is less than G is less than H. F is less than G is less than H. H and F go to 0, right? So the middle will go to 0. Is that clear? Yes, sir.
Do you think it would be possible to represent these as math?
Sure. This one? This question?
Yeah.
That's, I mean, this is a bit tough, but you can still do it. Okay, this is the line 2x minus 1. This is the parabola. Yeah? Are we good? And then, you have a function in between. Okay? Yes, sir. Yeah?
I'm wondering, sometimes for the theorem, graphically it doesn't actually squeeze our function as a factor. Are we going to see any differences?
What do you mean? No, here it does squeeze.
Yeah, in this case.
Yeah. If it doesn't squeeze, then you cannot use it. Right? If it doesn't squeeze your function between two functions that go to the same point, then it doesn't work. Yeah? Well, yes?
Is there any case where function on either side of the element, but it would make the function without
No. That's the power of it. Right? Yes. Where you? We're not using the product rule. No, I mean technically you can still use like a squeeze theorem, like if you can use the product rule, why use the squeeze theorem? Right? Is that clear? Yeah. Where the answer is 0. Okay. Maybe we start continuity and then I give an answer. Yeah. Guys, yes. Yes, cosine is bounded between -1 and 1, and sine is bounded between -1 and 1. you should know these bounds. You should know the remarkable values of sine, sine pi over 6, pi over 4, pi over 3, and all their, related numbers, adding pi over 2. You should know your trig formula, cosine 2x, sine 2x, all of this, you should know these. Okay? Yes? Usually, whenever you cannot use the limit clause, and you have something that is bounded, right? Cos 31 over x, it doesn't have a limit as x approaches 0. Great, but it's bounded. Okay? Now it's not a rule, right? But once you practice a lot, you will be able to spot, okay, here I need to use the squeeze theorem, here I need to use, okay? We will be doing more practice. Okay, great. Let us move to continuity now. Okay, great. Now, let f be a function defined near a point A, including A. So, near meaning an interval containing A. Well, for now, I mean, we don't have to. Then, we say that f is continuous at A if the limit as x approaches A of f of x is equal to f of A. So here I have three things. F is defined at A, the limit as x approaches A exists, and the limit as x approaches A of f of x is equal to f of A. Yes? Let f be a function defined near a point A, including A. Then we say that f is continuous at A. I missed an S. If the limit as x approaches A of f of x is equal to f of A. Okay? So there are three things that are implied here. F is defined at A. The limit as x approaches A of f of x exists. And the limit as x approaches A of f of x is equal to f of A. Okay? This is what I said now? Yeah, there are three things that are implied here. That f is defined at A. Okay? Right? It's clear that f is defined at A, right? F of A means that A is in the domain of f. The limit as x approaches A of f of x exists and is equal to f of A. Okay? Great. What are examples of a continuous? And how do you know, like, graphically, what does this mean? That a function is continuous. You can sketch its curve without lifting your pen, right? So basically, your function here is discontinuous. So pick a point here, say that this is 1, and this is f of 1 here. The y value is f of 1. The limit as x approaches 1 plus, right? X approaching 1 bigger than 1. What? Or x approaching 1 from the right, right? 1 plus, what is the limit as x approaches 1 from the right? It's f of 1, right? What's the limit as x of f of x as x approaching 1 from the left? It's also f of 1, right? Is f continuous here? Yes. Now, is f continuous here? So I have a graph. Is f a continuous function here? No. Did I lift my chalk? I lifted it, so it's not continuous. In fact, the limit as x approaches 0 minus of f of x is this number here, let's say it's 1. And the limit as x approaches 0 plus of f of x is 2. So that the limit as x approaches 0 of f of x exists. No. So, but f is defined as 0, right? F of 0 is 2. Okay? So f is not continuous in that case. Is that clear, everybody? Not continuous. Okay, great. Example. Well, here. Sorry. Suppose f and g are continuous. At a, then f plus g, f minus g, f times g, and f over g, if g of a is different than 0, are all continuous at A. Let's prove one of them. Maybe let's prove one or two of them. So the proof, let's look at the proof. What's the limit? What is that? By the limit laws. What is this? Let's prove. By the limit laws, how can I split this limit into a sum of two limits, right? What is that here? Now, if f is continuous at a, what is the limit as x approaches a of f of x? F of a. If g is continuous at a, what is the limit? Right? We see that? So is f plus g continuous at a? It is. Okay? Here, then f, g are continuous at a. Great. Now let's do the last one. What is that? By the quotient rule, by the quotient law, like the limit laws, I have the limit of a quotient, right? The limit of the top, does it exist? What is it equal to? F of a, right? The limit of the bottom, does it exist? G of a. Now, in order to divide f of a by g of a, what do I need g of a to be? Non-zero. By assumption, g of a is non-zero. Okay, is that clear? If g of a is 0, then that doesn't work. Okay? And f, g are continuous. So f over g is continuous at a. Great, awesome. Let's take another chart. An example of continuous function at every point in their domain are polynomials, right? Polynomials are, where is a polynomial defined? For any number, right? We know that? Yeah? a polynomial function is defined on R, right? Is defined on R. You know what R is, right? Have you all seen that notation? R is just the real numbers, okay? Is defined on R and is continuous at every point in R. Now, a rational function, do we know what a rational function is? What's a rational function? It's a quotient of two polynomials. Have we seen that? Okay, not many of you have seen this. A rational function which is a quotient of two polynomials is a rational function defined everywhere in general. So if I have the quotient of two polynomials, is it defined everywhere on every number? No. In general, I cannot say that it's defined at every number. What do I have to worry about? The denominator being 0. So it's defined, a rational function is defined at every place where the denominator is non-zero. Now, if I remove this point from the domain, if I remove the zeros of the denominator from the domain, can I say that the rational function is continuous at every point from its domain? We see that? Let's give an example after. It's continuous at every number in its domain. Let's give an example which will make it clear, I guess. Okay, example. Who wants to give me their favorite number? Favorite number, favorite number. Someone who hasn't raised their hand today. Okay, can't really remember. Okay, yeah, in the back, yeah.
42.
42, okay. -1, let's see, okay, over x squared minus 1. Well, let's not do that. No. No, that's fine. Okay, that's fine. No, I mean, that's okay, that's okay. Okay. Great. Is this a rational function? The top is a polynomial, the bottom is a polynomial. We agree? Now, what is the domain of this function? So please raise your hand. What is the domain of this function? The domain of this function, I want to see more hands raised. More hands raised, more hands raised. Yes, sir. Yeah. Except for 1 and -1. Can you help us how you got this answer? Exactly, right? And the numerator is defined everywhere, right? Yeah. So f is defined for all x different than 1 and x is different than -1. So what is the domain of f? The domain, you write this, x r, x different than 1, and x different than -1. Okay? Now for any a in D, f is continuous any A in D, right? We agree with this. The limit as x approaches A of f of x. So let's pick x equal 2, A equals 2. The limit as x approaches 2 of f of x. Isn't it equal to f of 2? Yeah? What is the limit as x approaches 2 of f of x? What is that? Well, what is that? Can you ask me? What is this limit? What is the limit of the top? It's 2 to the 42 minus 1 plus 2, right? And the bottom is 2 squared minus 1. This is by the limit laws. We agree or not? Is it equal to f of 2? Of course. So f is continuous at 2. Is f continuous at 3? F is a rational function. Is 3 the domain of f, everybody? Is f continuous at 3? Is 4 in the domain of f? Is f continuous at 4? Okay? Clear? Any questions? Any questions? Okay, so I assume that you all know how to find the domains of functions. So you need to know the domain of arc sine, arc cosine, arc tan. You know these or not? Tan inverse, cos inverse, no? Okay, great. Guess we'll have fun later. Yeah. Any questions on this? Yeah. Yeah, very good. You can also express the domain as a union of yeah. Yeah. You had a question? No? Any questions? Any questions? Yeah. Guys, please, yes. Pardon me? No. That, oh. Is that it? That's fine. If you use the square bracket or the that's fine. Yeah. Yeah. Oh, sorry. Yeah. What is A in D? This side? This side it belongs to, right? Have you seen this before? Yes. For any A belonging to D. What is this D? Any number in D. Okay? What's any number in D? It's any number that is different than 1 and minus 2. Yeah?
So like to follow that, if you have 1 or negative 1, you just compare these like 1 is not good.
F is not defined as A. Yeah. Exactly. So F is not defined.
So if we gave us the next one,
Yeah. Okay, any questions? Guys, any questions? Yeah. Guys, yeah. No, I'm just giving example of a continuous function, right? How do you find it? How do you check a function is continuous? Okay? Great. Have many of you seen this before? Oh, okay. If you have not seen that, then that's okay, right? You're not supposed to have seen this. Yes. Yeah. Can I? What do you mean the polynomial law? If I have it, guys, please. Exactly, I can plug in for polynomial, provided the denominator is not 0. Okay? Great. Okay. do one more exercise. Let's do one more example. Or you know what? I think we can call it a day. Have a good weekend.